Okay, so let me just recap before I get some questions. So what we did yesterday is first we said that we described what large deviations are, and then we characterized them by a rate or large deviation function. And the formal definition of a large deviation function was of some variable that takes the value a was minus the limit of n goes to infinity of 1 over n of log the probability. Or in other words, it means that the probability of observing the value a behaves asymptotically is e to the minus n times the rate function. And for a very simple example of coins, we calculated the large deviation function, and it took this very simple form for this problem of log 2 a log a plus 1 minus a log 1 minus a. And I want to stress that this is a very nicely behaved function. Somebody asked me a question at the end of the talk yesterday, and I sort of answered in a rash way without thinking too much. This is a well-behaved function, and all the issues with a equals 0 and a equals 1 actually were in the correction to this function. This is a very well-behaved function, and you know this part looks like the entropy of a hardcore gas, so you might recognize it from other things that you've done in the past. The second thing was I showed you one way of a method for evaluating large deviation functions. So LDF will be my short for large deviation function. And the idea was to use techniques which are very similar to changing ensembles in equilibrium stat mech. So we look at the generating function, and by tuning the coefficient in the generating function, what we do is select different values of the probability, and specifically different values of the rate function. And what I ended with yesterday were a bunch of motivations. And I did some from out of physics and some from physics. And I ended by saying that by a specific motivation, which will be the driving force in these lectures, I looked at a macroscopic system. And we know from statistical physics that, for example, if you look at a system with energy E connected to some bath, we know from statistical physics that the probability of observing an energy density epsilon in the bath, so that's given by E over N, where N is the number of particles in the system, say, or some degree of freedom, behaves as e to the minus n times beta times the free energy density at energy epsilon minus this correction due to the normalization. And I want to stress that if you go to a review paper, they write this slightly different than what I'm doing here, but the gist of the idea is exactly the same. And if we look at this, we identify this whole thing as the rate function of observing the system at energy density epsilon. And again, I want to stress that the whole structure that we're discussing has these, the similar structure to stat mech, where n is extensive and epsilon is an intensive variable. And the final thing that I did was I tried to argue that this whole thing, this exponentially small probability of observing a macroscopic system is related, and I haven't shown it rigorously, and we'll see it later today, is related to a dynamical picture. And the dynamical picture is that if I write an equation of motion for the energy density, then it has a deterministic part which pulls you towards epsilon star, but then there's a noise, and because we're looking at a system that's composed out of many, many degrees of freedom, and we can roughly think about these as breaking up into systems each of size psi, a correlation length, then we have a noise that scales as 1 over square root of the number or of degrees of freedom times some noise in the system. And that means that there's very small noise that's driving the system. And this 1 over square root of n is essentially a result of just summing over many, many degrees of freedom. So questions about the lectures yesterday?
Yeah, there is a raised hand.
Yeah, please ask.
Yeah, can you please repeat the reason of that 1 by square root of n part?
Yeah, so the idea is the following. We have all these different parts of the system which are acting roughly independently. Okay, so if I sum the contribution of the fluctuation in each of these parts, okay, then the typical value, just by central limit theorem arguments, the typical value of the sum will go as square root of n. And because we're looking at epsilon, which is equal to E over n, then the noise becomes 1 over square root of n. And if it's still not clear, then I'm going to derive it for a very simple example in a few minutes. Okay? There's another.
Thank you.
Yeah.
So in the definition of rate function,
Yeah.
Is it possible to have, can you go to the definition of rate function? So
Yeah.
instead of 1 by n, can we have some other function of n, like say 1 by n to the power 3 by 2 or something like that?
So there's the common case is 1 over n. There are some examples that people have looked at the more exotic powers. As far as I know, you need some time dependence in the problem, but it is possible. Okay, there's some more actually very recent works which show scaling of that form. Thank you.
There's also a question in the chat box, I think.
Okay.
Yes. So is there any relation or comparison exist between large deviation and standard deviation?
Okay, I'm not sure. So I'm not sure what you call a standard deviation, but standard deviations, just going back to the talk yesterday, I think what I would call a standard deviation is what the central limit theorem tells you. So standard deviations are one where, for example, the variable a scaled as 1 over square root of n. So it's very, very close to the mean. In large deviations, we're interested in a, which is of order 1. So that's how I would distinguish between what you might call a standard deviation and what you call a large deviation. Okay, remember when we looked at, I just remind you that when we looked for the simple case of the coin, at a equals to 1/2 plus epsilon, and we scaled epsilon with 1 over square, we took epsilon to be of order 1 over n, and then send n to infinity, we recovered the central limit theorem. Okay, there's another question by Ashan.
Yeah. In statistical mechanics, the probability part itself comes as e to the power minus beta e. But in this case, how did you gauge the form of the generative function as e to the power nks or nka?
Well, I didn't guess it. Let me go back. Okay, let me draw another picture. Forget about, I didn't say anything. First of all, I didn't guess anything about the probability distribution. We solved it for a particular case, and you'll see later that we'll actually have to use for dynamical systems. We'll have to actually use the dynamics of the systems to calculate the probability. But the only thing that I'm using is the structure of this generating function. So here I haven't really assumed anything about the probability distribution.
Not the probability, but the but the e to the power nk part.
Okay, so that's actually a standard form, and the idea is that if you have an increasing function, you just chop it with an exponential so that you have a peak at a specific value of k. But actually, in other fields, that's a popular choice in physics and much of probability theory. But if you go and talk, and the Technion has a large electrical engineering department, they actually replace the exponential by a step function. And it really doesn't change a lot.
Okay, so you want to say that beat any function, we will get the correct result at the end of the day.
Yeah, you just want to make sure that there's when you're calculating this thing, there's a nice saddle point. And actually the form of the saddle point, the function that you choose, if it's exponential or something else, is not really important, as long as it's picking up a specific value.
Okay, thank you.
And the same thing goes in StatMech. You know, I guess one example, when you do the microcanonical ensemble, sometimes it's defined on a shell of energy E, but sometimes it's defined all energy up to energy E, and it doesn't really change anything at the thermodynamic level. Okay, other questions? Okay, if not, then I'll move forward. So what I want to do before moving forward, I want to discuss, for those of you who want to look further than what I do in these talks, I want to discuss some references. So first of all, there's a large list of people associated with large deviations, people who have won prizes for their work on it. There's a lot of people in the mathematical community, and the most famous words that go with it, and what we're doing will be some variants of what they did, is Vardan and Friedlin and Wenzel, and there's a guy named Ellis who made the connection to StatMech very explicit. And there's a nice book which I like by Amir Dembo and Ofer Zeytouni, which covers the more mathematical aspects of what we're doing. And again, this is again, for example, the electrical engineering department, they have a few people who are interested in calculating large deviations with implications to engineering. Now, inside physics, there's a lot of recent literature, but I really want to stress there's really beautiful work that sort of foresaw much of the developments that are being explored today by Graham and Tell. And they were looking at finite dimensional Fokker-Planck equations with weak noise. And they're really beautiful papers. And much of what I'll do in these talks will be building on slightly more modern language, but really reproducing some of the results that they derived already back then. Then in the 2000s, what really sparked the renewed interest in the field is works by Bernard Derrida. Specifically, there was a paper by him with Joel Leibovich and Gene Spear, where they calculated the large deviation functional for the density for boundary-driven exclusion process, and found out that it's long range. And then the results of Bernard Derrida were cast in a different form by the Rome group. Which was included people like Bertini and Yona Lacinio, who really introduced the language that I'll be using today. Bernard Derrida, in the work that they did initially, started with an exact solution and derived from that the large deviation function. And the Rome group sort of used all these results from the mathematical literature in a very rigorous way to rederive the results by Bernard and obtain some new ones. So there's some nice reviews already out there, some of them quite old. So there's one by Bernard Derrida himself, and it's JStatMech, and I'll just write the reference for completeness, and it's 2007. There's one by the Rome group, and that's in Reviews of Modern Physics. And again, depending on your taste, you might want like one or the other. The closest thing to what I'm doing here can be found in a shorter review by myself and Youngju Baek and JStatMech P080265, and that has some influence on singularities and these things. And then I can't go on in discussing large deviations without referring to sort of an epic review by Hugo Touchet. It's in Physics Reports. And it's a very pedantic and pedagogical review, but the spirit is slightly different than what I'll be doing in these talks. So all these things are good references, and if you open the archives every week, there's quite a few papers on the subject now. And still many interesting things are being found. Okay, so I think I don't have to ask if there's questions about this. So what I'm going to jump in, and again, my motivation is to sort of prep you to reading papers about many-body systems. But it doesn't have to be, even if I think about an escape problem where I have a metastable state, then if the size of the barrier is much larger than the noise, then the methods that I'm describing are completely applicable there. And if I have time, I'll discuss it later in the talk. But what I want to discuss is the problem of calculating large deviations and the weak noise limit. And again, I want to do everything in a very, very simple problem. So what I'm going to do is I'm going to take independent harmonic oscillators. Okay, so this is very boring, but hopefully the techniques will keep you interested in the problem. So if I look at one oscillator, then I can write down a Fokker-Planck equation for its probability distribution, and I'm going to look at a one-dimensional harmonic oscillator. So we have some diffusion coefficient, which I'm denoting by gamma. And this is my Fokker-Planck equation. And I'm going to look at the potential, which is just the harmonic potential. Okay, so this is something that we all know how to solve for the steady state, and even more than the steady state. It's a linear problem. And it's really easy, I hope. If somebody insists, I can derive it, but it's really easy to find that the probability distribution is equal to mu kx squared divided by 2 gamma. And if we take gamma to equal to mu t by the Einstein relation, then you recover that this is equal to e to the minus beta v of x. Okay, so this is all something that I assume that you all saw before. There's another way of describing the same problem, same physics, and that's through a Langevin equation for the harmonic oscillator, which is given by the velocity is equal to the force acting on the particle plus a noise whose amplitude is 2 gamma. So just to make sure that we don't mess up the notation, what I mean by this is that I draw eta from a Gaussian, random Gaussian distribution, and the average of eta is 0, and the 2-point correlation or the covariance of eta in my notation is just delta correlated. Okay, so this is all boring, sorry for doing it, but what I want to do is I want to do an independent. And hopefully towards the end, we'll discuss, or at least I'll give us homework, some more complicated problems. So we're taking n independent oscillators. So we have oscillator 1, 2, etc. And each of them has location x1, x2, and up to xn. And the equation of motion for each of them, and I'm using the Langevin equation, is given by the usual form. And the only thing that I have to specify is that I'm assuming, just again, just to keep things as simple as possible and focus about the methods and not technicalities, I'm going to assume that the oscillators, the noise on the oscillators is completely uncorrelated. Okay, so I remind you we're interested in large deviations, and we're looking at some intensive quantity. So intensive quantity. And what I'm going to choose quite naturally is the average location of all the oscillators. And what I want to do is evaluate this thing. We know the solution. I'm going to write it in a second, but I want to evaluate it using a sophisticated method. So first of all, I want to write down an equation for x. So x dot is equal to 1 over n times the sum from 1 to n of xi dot. And if I sum over all these equations, okay, let me do it just so I'm not too quick. So I'm just summing over all these guys. Eta I of t. Okay, and you can see that this guy just generates a minus mu kx. And I have this funny noise term, which is a sum over all these random noises from each of the oscillators. Okay? So what I can do, I can define a new noise, eta bar, which is equal to the sum of I equals 1 to n of eta I of t. And because these are all Gaussian variables, then this is also a Gaussian variables. And we can calculate the variance of this guy. And the variance of this guy, so eta bar of t, eta bar of t prime, is just because each of these etas are uncorrelated, we're just left with contributions from the same oscillator. So we're left with a bunch of sum over the delta functions of t minus t prime, which is equal to n times delta of t minus t prime. So this is exactly what I was arguing for heuristically before. When we sum over random contributions from each of these small boxes, then we get a noise whose amplitude is generically square root of n. Okay? So the amplitude of the noise of eta bar, sorry, amplitude of eta bar is square root of n. So it's natural to define eta of t, which is equal to square root of n times eta bar of t. Okay, this is just a definition. And if I do this definition, then I can rewrite my equation of motion as 2 gamma over n times eta of t. Okay, so is that clear? And eta is just delta of t minus t prime, the correlator of this guy. Questions so far? Because I haven't checked that you're awake for a while. Everything's clear? Somebody say yes?
Yeah.
Okay.
This n is under the square root, right?
The n is under the square root. Yes, thank you. I should have written it more clearly. Yes, so the square root extends all the way here. Okay, so by looking at a lot of oscillators, and the same occurs for an interacting many-body system, when we look at the sum of many random variables, then naturally when we look at an intensive quantity, then we have small noise, and we can easily solve this equation by writing down the Fokker-Planck equation. So exact solution, in our case, using the Fokker-Planck equation, I'll just write it out quickly to make sure that we're all on the same page. And the only difference from the previous equation is now that we have this 1 over n that appears here. So I just copy the previous solution with a small modification, and I found out that the steady state probability distribution is given by this expression. And that means that if I write this as e to the minus n times my rate function, then the rate function for this very simple problem is mu kx squared divided by 2 gamma. Okay, and again, by using the fluctuation dissipation relation, you get the same old result. Okay, so far I haven't done anything fancy at all. All I've done is just standard statistical mechanics of harmonic oscillators, and the only new thing that I've done is summed over many. And again, the only implication of this is that you get that the probability of observing a value x is exponentially small with a number, the value of x which deviates from the mean is exponentially small in the number of oscillators. And the more oscillators you have, the faster the probability decays, which is not unexpected. Okay, so what I want to do is I want to rederive this method by a much more, not much more, but a more sophisticated method. And what I want to stress is that, again, this is a very simple problem. And the only reason that I'm choosing it is to focus on the method and not technicalities. So what I'm going to do is I'm going to solve this oscillator, so sort of like killing a fly with an elephant. I'm going to solve it using path integral methods. And I'm going to do 2 path integral methods. Sorry, my pen doesn't want to write something. So the first will be a Lagrangian approach, and the second will be a Hamiltonian approach. Okay, and I'll explain everything in more detail. So let's go back to the Langevin equation that we're looking at. We're looking at a Langevin equation of the form x dot is equal to v of x. So this is just to save me from writing minus mu kx everywhere. And then we have this noise, which I call gamma tilde, which in principle can be a function of x, times eta of t, and you know, at least from Sanjib's notes, I think that you've been told that if you write, you can express the transition probability to reach x final at time t final, specifically, and I've absorbed, there's hiding here, is that I've started at time 0 at point 0, and we'll get back to that later. I can write down the transition probability as a path integral. And here I'm summing over all paths. And the form of the path integral is the integral from 0 to tf of dt prime of x dot minus v of x squared divided by 4 gamma tilde, which in principle can be a function of x. If you don't remember how this is done, remember eta is a Gaussian variable, so all I have to do is write eta equals to x minus v of x divided by square root of 2 gamma, and I just plug it into the Gaussian distribution, and I have this this form. And there's a small Jacobian that you have to take care of, but it's 1 in this case, especially in our case where, okay, it's 1. Let's just leave it at that. Okay, so so I have my my path integral representation for the transition probability, and for obvious reasons. Okay, so remember that gamma tilde was equal to gamma over n, where n is the number of oscillators. So with this in mind, what I'm going to do is rewrite this transition probability as the integral from 0, 0 to xf tf. Sorry, let me just clean my notation. xf tf of over all histories of e to the minus n times something that for obvious reasons I'm going to call an action, and the action is given by the integral from 0 to tf of dt prime of, sorry, my brackets are too large, x dot plus mu kx for our problem, square divided by 4 gamma. And with this, I can identify a Lagrangian, which is a function of x dot and x, which is given by x dot plus mu kx squared divided by 4 gamma. So this is, this guy I call an action for obvious reasons, and this guy I call a Lagrangian. Okay, any questions so far?
Yariv,
Yeah.
I guess you're ignoring the Jacobian because of this 1 by n term, right? Because this quadratic term Jacobian will be still it's not 1, it will be some exponential of, it will relate to the v prime basically.
So there's 2 reasons for ignoring the Jacobian. First of all, we're interested here in rate functions.
Yeah.
All the Jacobians will give subleading corrections.
Yeah.
Okay, and the other thing that if we're doing Ito calculus, the Jacobian is 1.
Mm-hmm.
Okay, so but the simplest reason is, okay, I can even elaborate. I can make this more complicated. So first of all, the Jacobian is subleading. The second reason is that for Ito calculus, the Jacobian is 1. The third reason, and I'm not going to do it, that for weak noise problems, it actually doesn't, somewhat for the reason that I said, that it's subleading, there's no difference between Ito and Slatanovich, for example. Mm-hmm. Okay, so you don't have, for these weak noise problems, you don't have to worry. It's actually hidden in my answer that you don't have to worry about Ito or Slatanovich. Okay, so so we have this form. We have this form and I remind you that n is large. So if you see something like this, what can you do? This is, someone should answer me. Okay, just to hint, this is equal sort of to 1 over h bar, dimensionless h bar. Okay, so what can you do if you have a large parameter in front of in a path integral like that?
Take the saddle.
Sorry? Saddle point.
Lagrangian.
Okay, so we can do a saddle point. Okay? Okay, so since n is large, can get leading order behavior in n using a saddle point approximation. Okay, and again, when n goes to infinity, it really becomes exact. So we're basically we basically have an analytical mechanics problem. We minimize the action. Okay. Action. Okay, sorry. We minimize the action. We find the path. Okay, so let me be more explicit. So to do, what we want to do is find most probable trajectory, which is characterized by a specific solution of xt. So this is, in other words, the most probable most probable history. Okay, so we find this x as a function of t, and once we find it, plug solution into action, okay, and get the probability. Okay, so if it's not clear, I'm going to do it explicitly in a second. Okay? So specifically, my large deviation function, will be, so LDF will be the action starting at 0 at time 0, and you have to worry about the initial conditions, but I'm going to ignore that in this for the moment and hope for a question about that. So we're looking for the history that minimizes the integral over time of my Lagrangian. Okay, so how do we minimize the action? Which equations do we use? Sorry, I don't see you guys. So I need some feedback to know that you're alive out there.
Euler-lagrange.
Okay, great. So that was Omer, right?
Yep.
Okay, so others should also participate. Okay, so we minimize this by using, so to minimize, we use the Euler-lagrange equations. So specifically, just to remind you, we take a functional derivative of the action. So we have, sorry, let me write this in a clean way. Let me not rush. So d dt of dl dx dot plus dl dx equal 0. Okay, so that's the problem that we want to solve. So let me just recap what we did so far. So in the large, what I've said so far, large n limit, given that a fluctuation which leads to xf at tf occurred, then it is dominated by a single history. Okay, so the idea is that all these oscillators have to do something completely crazy in order to reach this rare event, and really there's one history which is so much more probable than all the other histories that when we take the large n limit, that's the only history that we see. So that's one of the take-home lessons from these lectures, is that if you have a many-body system and you're looking at how a specific fluctuation occurs, then it's actually a deterministic, there's a deterministic way. So if you remember, I told you that people were looking at using this for looking at climate, extreme values of climate, specifically the guy who did it numerically. A really beautiful effort by Freddy Boucher and his group. And what they look at a fluctuation that creates a heat wave, and then given that they know that this fluctuation occurs, they can tell how it occurs, how its history evolved, and how the most probable configuration looks. So where is it hotter, where is it colder, etc. Okay, and that's a general property of many-body systems. Okay, so again, we have our action. Let me just remind you, we have our Lagrangian, which is this guy, and we can use the Euler-Lagrange equations, and I'll spare you the math because we're a bit short on time on these lectures, and the equation of motion. So after Euler-Lagrange, for these oscillators, we have x dot dot is equal to mu k squared times x. Okay, so that's so notice it's just a classical, just analytical mechanics of that's associated with this stochastic process, and we want to use this to obtain steady state distribution. So how would you go about calculating the steady state distribution? Remember, we're calculating the history between time 0 and TF. So to obtain the steady state distribution, what would you do? Someone?
Put TF to infinity.
Yep, perfect. So if I take TF to infinity, then I'm at the steady state by definition. Okay, I'm doing it in a sort of funny way. If you look at most calculations, people start at minus infinity and end at time 0. But what I'm going to do is I'm going to take TF to infinity for the moment. So what I'm looking for is a solution that starts at time 0. And I'll ask a question about this in a second, at 0, which is the most probable configuration, and reaches at time infinity position x. Okay, so when you look for a solution which satisfies these boundary conditions, and again, I'm just skipping the simple math. It's just second order regular differential equation. And you find out that the solution is given by this. So what you find out is that and I'll discuss it in a second, that the particle is basically next to the origin for a very, very long time, and then shoots up towards the end, towards the final position, xf. So I should have denoted this xf to stress that it's the final position. So now we've obtained the most probable history of the fluctuation. And what I want to do is show you that you can use this to calculate the steady state. So what I'm going to do, if you're writing with me, you're not going to like it. So we have this guy, copy. So what I'm going to do is I'm going to plug in the solution inside this. So when I plug in the solution, I get 2 mu k xf e to the minus k tf minus t. And the next simple step is just calculate the action associated with this history with tf goes to infinity, and that's given by 0 to tf of dt of xf squared mu k squared divided by gamma e to the minus 2 mu k tf minus t, and you do the math and you find xf squared mu k divided by 2 gamma. So in the steady state, we have that the probability of observing, I'm dropping the f, so the probability of observing the system at position x is given by e to the minus n x squared mu k to gamma, which is, as before, better be. Okay, so it's just a very, very sophisticated way of obtaining, it's sort of an overkill for this problem, of course, but it's a method that's much more powerful for more complicated problems. Even though there are methods using directly the Fokker-Planck equations, this one in many cases is very, very useful. What I want to note is that the solution is 0 except for a period of time which is given by 1 over mu k. Remember, our history is e to the minus mu k tf minus t, and therefore this whole exponential means that everything's changing only on this very, very, very short time interval. So this is a short time interval. And what this means is that if I plot x of t as a function of t, and this is tf, then it really looks like this. It just shoots up, but only at the end. Okay, so the time interval here is 1 over mu k. And for the reason that things are happening only at the very, very short time at the end, people call these objects instantons. Okay, because everything's happening extremely fast towards the end. And the reason that it's happening towards the end is that if I have my particles, my weak noise system sitting at the minima of the potential, then any excursion that would happen at an earlier time will cost a lot of action. And remember, in the large n limit, there's really one history that dictates it, and it's the one with the highest probability. And the highest probability is one that just sits there doing nothing until the final time, and then it just shoots up. It remembers that it has to go up, and it just shoots up on a very, very short time scale. Okay? So questions?
So isn't T always smaller than TF?
T is smaller than TF, yes.
And how come it will, this xt will diverge as a function of T?
doesn't
Because
diverge.
it can at max go
No,
up
no,
to T, right?
diverge. This is actually here. This is X final. Okay? It just rises very, very quickly. Look at the solution. The solution is here. Okay, so its time equals to TF. It hits XF. Okay? Okay, everybody's with me? Questions?
But why is 1 by mu to the power k small? Is it by choice or?
Well, it's just a number in the model, and n is large, right? And these are just numbers. So unless I fine tune it so it goes to 0 in some funny way, then it's generically a very, very short time compared to this infinite time that we're looking at.
Yeah. So that's for particular choice of for the values of these parameters, right? Only if you choose them to be very.
I think you have to choose it in a really funny way if you want to have it drag over an infinite time. Okay, you have to do some limiting procedure. If you just treat these as numbers, then it's never going to be a long time. You see, even if it's 100 years, then you know, compared to infinity, it's nothing. And we're interested in the steady state. Okay?
Okay.
So it's called an instanton in contrast to something, I think that might help. You know, you could imagine a history which does all these things, that changes and then reaches this guy. Okay, so that's a possible history. It's definitely some history, but this guy has such a smaller probability compared to this one with the instanton that we just never see it. Okay?
So can you explain
Okay.
it physically again?
Yeah.
Hello.
Question.
Yeah.
I can't hear you.
Can you explain it physically again? Instantons.
Yeah, so the word instanton, it's just a fancy name of saying that this oscillator with the weak noise, if you look at its history, it's sitting next to the minima all of the time, the most probable history, which is actually the one that you observe given that it dominates the leading order of n behavior. So if you have a weak noise system, it's what you observe. It just means that if I'm interested in seeing the oscillator at time tf at position xf, then the most probable history is one that sits here almost for forever, and then in a time interval that's 1 over mu k, it shoots up and reaches this location. Okay, so it's called an instanton because all the action is happening towards the final time that you're interested in.
Okay. Okay.
Okay, so it's just a fancy word for saying that everything's happening. And the reason is that if this guy would bounce about, then the cost in action, remember, we just have a mechanics problem. The cost in action would be so large that the probability of observing this compared to the history that we can calculate is just completely negligible.
Yeah.
Yariv?
Yeah.
So isn't it an inverted oscillator? Well,
No, this is for quantum problems.
no, the equation.
The equation, oh, the equation Oh, the equation of motion? Yeah, it's for an invert. Yeah, the equation of motion has momentum, right? I didn't discuss it, but you're right. Yes. Okay, I'm skipping this detail, but yes, it's not the usual. You know, it's not our damped harmonic oscillator equation of motion, definitely. Okay. And okay, I'll try to give a better physical interpretation when we discuss the Hamiltonian formalism. Okay. Other comments, questions? Okay, so I think it was Abhishek, right? He pointed out that if you look at this equation, it's an inverted classical harmonic oscillator with inertia. But I remind you that we haven't even looked at the problem with inertia. Okay. Okay, so there's another interesting question that you can ask. So interesting, and I'm going to use that in a second. What is the most probable path for relaxing to the most probable configuration? So specific, the most probable configuration is where x is equal to 0. So again, we have our equations of motion. X dot dot is equal to mu k squared x. Okay? And the thing to notice is the equation. Okay, something's going wrong here. So the thing to note is that the equation is symmetric under time reversal. Okay? Right? If you look at this, if you want a harmonic oscillator with inertia, then the equation of motion is symmetric under time reversal, and that implies that the relaxation is the time reversed trajectory. Okay, and this is, as I'll show later, this is a direct consequence of the fact that the system. Can somebody guess why is this the case here? Why is the trajectory for creating a fluctuation exactly the same from the relaxation one?
Equilibrium problem, that's right.
Sorry?
It's the equilibrium problem, sir.
Right, perfect. And that's the reason that we're dealing with an equilibrium problem, which has a time reversal symmetry. Okay, so that's a property that once we look at non-equilibrium systems, we'll see that it breaks down. Okay, and can somebody tell me what the action for the relaxation process will be? Okay, I'm going to leave it as a small exercise, but can somebody guess? If I start here and I ask how much action does it cost me to just slide down here? What's the cost of the downhill, of going downhill?
0.
Yep. Okay, so going downhill, no cost in action. Okay? Okay, questions? Something. I'm not continuing until I have one question. Okay, I don't think I'm moving forward until there's a question.
There's a question in the chat box.
We started from the overdamped equation. You're absolutely right. And one way to realize why we need a second order in time derivative is, remember, we're solving a differential equation with a fixed initial and final positions. So we really need a second order differential equation to solve it. You can think about it as an analytical mechanics problem where you want to shoot the problem at time equals to minus infinity with just the correct velocity, so that in the right direction, so it reaches at times TF, it reaches the position that you're interested in. Okay? And again, this all came from this minimizing this action. Okay.
Sir, I have one question.
Yeah.
So how to choose that velocity, like such that particle at time tf reaches xf?
Well, that's what we did. Okay. So let me try to be. Yeah.
No, I was suppose I want to do this in simulation. So I was wondering, like,
Okay. So what you do?
What should be the?
Let me get back to that in a second. I just want to clarify. So one question that should come about is the downhill trajectory. We expect it to just be this guy, right?
Yes.
Okay, so let's differentiate this guy again. So we have minus mu kx dot, and then plugging in the equation of motion, we get the same equation that we had before. Okay? Is this clear? So now your question about, okay, I might have caused some confusion. Any questions about this? So what you do in the numerics, typically you do what's called a shooting algorithm. So of course in the numerics you can't go to time t goes to infinity. So you look at a long interval of time, and because these are instantons, then eventually the corrections from the finite time are not so crazy. So what you do is you start changing, you start scanning the initial velocity, okay? And you just scan until you find out that you reach at the final time the position that you're interested in getting, okay?
That's like trial and error.
Yeah, just scanning in a careful way, not completely randomly, but scanning in a careful way. So to solve these differential equations, the method is called the shooting algorithm. So there's a question by Francesco.
Hi, Yariv. Yeah, I'm here. Can you hear me?
Yeah.
Okay. I was just wondering one thing. So I think that here things are nice and tidy because the Lagrangian is quadratic, so we can somehow minimize it properly, and we can get nice results this way. I was wondering if the Lagrangian was not quadratic and somehow there was some sort of metastable state. In that case, how would the instanton feel the presence of such a metastable state? Would we still have that all the effort is done by the end, or I don't know, maybe it's
a wonderful question, and I promise that I'll address it later.
Okay. Thank you. Yeah,
I promise that I'll address it in a much more careful way. You have to be when you have several states and one of them can be metastable, then you have to do things more carefully. The short answer is that the transition between a metastable state and another state is governed by an instanton. But when you calculate the probability of being in the metastable state, you have to be a bit careful, and I'll teach you how to do that.
Okay, thank you.
Okay, so if we have random k's, will this instanton effect be seen? Well, again, the way to think about it intuitively, the way to think about it intuitively is that you want to do something very, very rare. And okay, let me try to rephrase myself. So whatever you do, if you can write your problem, and I have to think about it in a more careful way, in terms of minimizing an action, you might have for your random oscillators. Let's look quickly. So instead of k times the sum of x, I don't know, I have to think about that problem, but if you can write it in terms of an intensive quantity, then yes, the instanton picture will emerge. And the reason is very, very simple. You know, the cost of a trajectory is just written, the cost of a given trajectory is just this exponential of this guy. And if you have an n sitting in front of the whole thing, I don't think I have the equation, but if I have an n here sitting in front of the whole thing, then it's just one of the guys will dominate, and it's clear, and I'll show it in a slightly different way later, and it's clear intuitively, but we will argue for it more carefully later, that anything that's not in the minima most of the time, something that wiggles about or does something crazy, there will be a cost in the action. Because deviating in the action from the minima of the action costs you something. Okay, so you're just picking the easiest way of doing it, and the easiest way of doing it is just spending the minimal amount of time away from the minimum. And that's what leads to these instantons. Okay, so just to recap, sorry, I forgot today to unplug my telephone. So just to recap what we've done, I've first calculated the trajectory for going uphill, and I think Abhishek pointed out that an upside down oscillator, which was a bit obscure at this point. And what we saw is that by solving this equation and plugging the solution and looking for the cost of this trajectory, we obtained exactly in the long time limit where TF goes to infinity, we obtained exactly the steady state distribution that we know from the Fokker-Planck equation, and we better obtain that, otherwise we're in trouble. And then I looked at the downhill solution, and the downhill solution, as I pointed out in the last point, is just hiding, just gliding down without any noise in the problem going towards the minima. So it's really the same problem. And what we saw that in this problem, the history of going towards a fluctuation, which is commonly called uphill, is exactly the same as the history of going back to the most probable state, which we call a downhill trajectory. So just before closing this thing, I want to ask you a question. Suppose that I take my problem of my oscillator, and instead of starting at the most probable configuration, I start at some x0. So what will happen to the solution? How will the solution look? How would you guess that it looks?
I think it will satisfy this Newton's equation of motion, right?
Okay, okay, so let me, okay, so it will satisfy, it definitely has to satisfy this equation, which we obtained by minimizing the Lagrangian. But what will happen is that this guy will very, very quickly on a time scale, which is 1 over mu k, will slide to the minima. The cost of this part, because it's going downhill, will be 0. And then it will stay next to the minima almost until the final time. And then at the time 1 over mu k near the final time, the guy will shoot up using the instanton. So in fact, if we start from any initial condition that's not the most probable, the results will be completely unchanged. It will just make the solution a bit nastier. And therefore, what people typically do is calculate the steady state probability by starting at the most probable configuration. Okay? Further questions? I really need some more feedback from you guys because I'm talking to the screen with black squares and I have no idea if I'm talking to myself. So please ask questions, especially now is a good time before I go into the next method.
Maybe things are clear.
Okay, hopefully. Okay, so far I've gone through the Lagrangian method, and what I want to do now is describe the Hamiltonian method.
There's a question in the chat box.
Yes. Why should there be noise in the uphill? So let's look at the equation, the Langevin equation. Let's go back to the Langevin equation. So this is my Langevin equation. If there's no noise, then I can only go downhill. So actually, the only way that I can move from the most probable state to a fluctuation is by using noise. Okay? Okay, so really, if you don't use noise, you just slide down. It's just the downhill trajectory, and you're stuck there. You can never leave the trajectory without noise. Okay, so now I want to discuss the Hamiltonian method. And again, my starting point is the Langevin equation. And again, I'm just helping myself with slightly simplified notation. And what I want to do is I want to derive a different form of a path integral. And there's a shortcut to getting to it, but I'm actually going to follow this form because it's very useful. And this form is a Martin-Segia-Rose method. And the idea is to write the transition probability, and again, I won't suppress it, to reach xf at times tf by averaging, let me write it down and explain, x of tf equals xf by, okay, let me write it down and explain it. Okay, so what I do is I average over all histories of the noise, and what I do is I make sure by this delta function that I'm satisfying that, that when I do my path integral over all histories, that I'm satisfying these equations of motion. Okay, so formally, this is just a funny way of writing the transition probability. I average over all possible realizations of the noise eta, and I run over all the histories of x, and I make sure that that my equations of motions are satisfied. And again, this is a functional delta function, meaning that at each interval of time, I have a delta function. Okay, so there's a trick of turning this into a useful path integral. And the trick is to write the delta function as a Fourier representation. Okay, so this is just the normal Fourier for a path integral. Okay, and the only funny thing that I've done in comparison to the usual path integral Fourier representation is, first of all, is that I've pulled out a definition of n. So x hat is the analog of what you usually see as k. And also, instead of having an I outside here, I'm running over imaginary values of x hat. Okay? So this is just a representation of the delta function. And what I can do, question?
Why n in the exponent?
This is just a convention. I could start with x hat tilde and then redefine a new variable n times x hat. And that will come about because I'm going to do a setup point on this thing. And I'm going to also give an interpretation for this noise term. Sorry, I'm running ahead of myself. I'm going to give an interpretation for this x hat variable in terms of the dynamics. Okay?
Okay.
Okay.
One question, please.
Yes.
The integration, is it about x or t?
The integration, here it's a functional integral over histories of x hat. So there's an
exponential
for each time interval. And here it's an integral over, oh, sorry, thank you.
Okay.
Now I understand your question. Thank you very much.
Yes.
Thank you. Other questions? Okay, so I plug this in and I have the transition probability, and I'm just dropping the 0, 0 notation. And then I'm just copying this. Okay, so sorry. So let me write it down, and I'm actually very short on time, so I'm going to leave it as a small homework exercise. So I'll help you a bit. So what you do is you take this path integral, you plug it inside here. So let me do this one step. So let me move this down. Let me do this one step. So we have P transition is equal to the average over noise over dx, and I'm just being lazy with the boundaries of the path integral. And I have e to the minus n, the integral from 0 to tf, dt x hat times x dot minus v of x minus square root of 2 gamma over n times eta of t. And now all I have to do is average this guy over all realizations of the noise whose probability is proportional to e to the minus integral from 0 to tf of eta square of t over 2 dt. Okay, so that's the probability of the noise, and that's a Gaussian integral that you can do. And what you find out at the end of the day, that you obtain this path integral, which takes now a Hamiltonian form. Okay, and when you do the math, you find out that the Hamiltonian is equal to x hat phi of x plus gamma x hat square, which in our case is mu kx x hat x plus gamma x hat. And if I look at this path integral, then what I can read is that this guy is like a momentum. Okay, and we better give it some physical interpretation in what follows. Okay, so it's just another way of writing a path integral. There's a small price here compared to the previous version that we introduced. We introduced this extra variable, which looks like a momentum, but we gain the Hamiltonian formalism. Okay, questions about this? So just to make this clear, the transition from here to here is a very small homework. Questions, please.
Sir, I have one general question.
Yeah.
I think like this appearance of x dot here is because of the fact that we started off with overdamped Langevin equation.
Right.
Yeah. Then in the underdamped case, what would happen?
In the underdamped case, well, you just repeat the same procedure, and let me think. I haven't thought about that. We have an x hat x dot dot. We have an integral dt. So it takes off a slightly different. It doesn't take the usual form. It's a more complicated problem. Okay.
Yeah.
Okay. Similarly, I think maybe somebody in the audience knows the answer. I think that your question is a bit similar to if we have the Lagrangian formalism. If you have an x dot dot, then the whole simple analogy to mechanics is a bit ruined because you have to do variation with x dot dot as an extra variable. Okay?
Okay.
Does that answer the question?
Yeah.
Other questions? Or if you want to insist on this one?
Hello? Sir, yeah, so this momentum runs along the imaginary axis, right?
Right.
So what is the physical meaning or whatever interpretation?
We'll discuss that later. We're doing saddle point calculations.
Hmm.
And that will be important later. Remind me of that question later, okay?
Yeah.
The
Thank
answer
you.
is we're going to do a saddle point approximation. On the saddle point solution doesn't have to sit on the axis. When you actually look at corrections, for example, beyond the saddle point solution, it's actually crucial to remember that it's an imaginary variable. Otherwise, you get nonsense results.
Okay. Yeah.
So,
Thanks.
so how we'll do it will be transparent. You won't have to worry about it. But really, when you look at things which are slightly beyond what we're doing, actually remembering that this is an imaginary guy is important. Okay. Other questions? Which approach is more useful? Okay, good. Great question. As you know from analytical mechanics, the Hamiltonian structure brings with it a lot of formal results that you have. For example, the Hamiltonian is conserved if you don't have time dependence in the equations. You have the Liouville's theorem, and all these things will be very, very useful, hopefully in the talk tomorrow. Okay, so the Hamiltonian structure brings with it a lot of analytical structure that's very useful for thinking about the problem. In terms of calculations of the saddle point, I don't have a clear winner. I've done both in my life. Okay, other questions?
Yeah, I've got another one on the instanton.
Yeah.
So I was wondering if that picture, like idealistic picture of the instanton, as the effort coming only by the end of the time window,
Yeah.
would work even if we were looking at observables which are different from the position and are multidimensional. I was thinking more like at the density profile, like the empirical measure, the empirical occupation measure. Would that work even in that case?
Okay, okay, that's a very good question. So if you look at something like a density profile of a macroscopic system, then the picture is very similar to what we're looking at. The system sits most of the time at the most probable configuration and then shoots up to the fluctuation at the end. There are observables like the time average curve. So in this case, in this simple problem, I guess I could look at the probability. So let's do an example. For example, I could look at the probability of the integral of x dot being equal dt being equal to some value. Okay, so that's another class of questions that you can answer. And in this case, actually, things behave slightly differently. And what you have is that you have typically, there are some cases where it's more complicated. Typically, the system very quickly relaxes to a time-independent configuration and stays there almost until the end. And that's because this A is an extensive quantity. It grows with time. Okay, so we want probably the one over the time that I'm looking at.
Okay, thank you.
Okay, so it's a very good question. There are observables where this instanton picture is not what you use, but still the idea of the most probable configuration, realizing the variable that you're looking at is the whole methodology is almost the same thing. Okay, you just add, okay, I won't discuss it, but you add essentially, you calculate the generating function of that extra term that you're interested in, and that leads to, and you minimize the action, and that doesn't give an instanton, it can give you a flat profile, for example. So a classic example is current large deviations, where that happens. Okay, other questions? Okay, so I think I'm out of time, and now we have a Hamiltonian version. So I'll just summarize with what we have to do. We have to solve Hamilton's equations. So we have to solve minus dh dx, sorry, and then x dot is equal to dh dx hat, and we minimize the action. We solve for the analog of the momenta in the position. We solve, we plug this into the action, and we get the cost of the trajectory, and we can repeat the whole thing and get exactly the same result that we got with the Lagrangian approach. I'll sort of go through it quickly tomorrow, and in particular, the reason that I'm going through it is that I'm going to give an interpretation to this variable, this analog of the momentum, And what I'll argue is that this analog of the momentum actually, once you solve the saddle point equations, represents the most probable history of the noise up to some coefficients. Okay, so x hat, the behavior of x hat, really tells us about how the noise acts when we're realizing the fluctuation. Okay, so maybe a few last questions before we finish, and then we'll resume tomorrow. Comments by Abhishek, Sanjib?
Yeah, I guess. I don't know. You are again going to put this thing today, right? This notes. You are going to send it, right?
Yeah, sure. I can send these notes, no problem.
Yeah. Even if you, yeah, rough copies are also okay, I guess.
Yeah, I can. I'll do that. Yes, no problem.
So I just wanted to say about this, this solution that, which for a long time it stays very small and then suddenly grows. So I guess it's, one way to think would be maybe, so you are really solving the inverted here, right? Because it's with the plus sign.
Yes, but that's
So,
for,
then,
but that you're giving it interpretation in terms of a harmonic oscillator with momenta.
yeah, right, yeah, I'm thinking of the harmonic, like the second order equation.
Yes, okay, I was trying to avoid that.
Yeah, okay, yeah, you're thinking of the overdamped, so, yeah.
Yeah, because it's an overdamped problem, and you're absolutely right that it's useful to think of this as a mechanical problem, but I think that it is, when you go through these things the first time, because there's no real momenta in the problem, right?
Right, yeah. No, but if like in the action, so basically you want to start with, have a solution which starts from the origin and goes to some point in a finite time, right?
Right.
But in a finite but very large time, you want to go to a finite distance. So which means you have to start with the extremely small velocity.
Yes.
And that's why it essentially stays there for a very long time and then it goes downhill very fast.
Yes, okay, I'm happy with this addition, yes. I take your point, thank you.
So in this case, it's also exact actually, right? Because the quadratic, this thing, the saddle point is actually exact.
Just because everything's quadratic, it's exact.
Yeah.
Okay, but that's very peculiar to this problem.
Yeah.
Okay, any other questions from the audience?
Non-quadratic Lagrangians you would handle within perturbation theory?
Well, if you're lucky, you can solve them exactly. That's what Bernard Derrida and Niona Lacinio did. You could do numerics for these things. In some cases, you can use perturbation theory. You have to think in what, and okay, depending on how much I get through, I might discuss a case like that on Thursday.
Okay, thanks.
I think there's a question in the chat box by Arga.
So it's not all, no, so again, so there's a question, x going to xf implies most of the oscillators have moved to xf. No, we're looking at the average of all the oscillators together. So once I'm looking at the equation for the intensive variable, then I've lost all the information about the individual oscillators. Okay? I really can't say anything about that. There's no information, I'm just looking at an equation for x. Okay, other questions? So again, if you have time, try to derive for tomorrow. It's really a simple exercise. Try to derive the Hamiltonian action. I will say that there are generalizations of this for non-Gaussian processes, and the Hamiltonians typically look pretty nasty for Poisson processes. Instead of this analog of the momentum appearing, there's e to the momentum. But sometimes you can make a lot of progress even with these nastier Hamiltonians. Okay, so tomorrow, yeah.
No, I just have this thing. No, do you find it easier if the person who is asking question keeps the video on, or is it's okay?
As long as people ask questions, I'm happy.
Because otherwise you don't see anybody and everybody sees you.
Yeah, it's a very strange feeling. So as long as people ask questions, I'm happy.
Okay.
Okay. Any other question? Comment?
So one other question was, so this this thing was developed in this 80s paper, is it?
So no, the 80s papers actually, what they did was work mostly directly with the Fokker-Planck equation, and then do a saddle point method using, like what you learn in your second course or first course in quantum mechanics with the Schrödinger equation. So what you do is you plug in a solution in the Fokker-Planck equation, which looks like this, and you look at the leading order behavior. So that's another method. Recently, there's been more use of this Hamiltonian and Lagrangian, but definitely working with the Fokker-Planck equation has its merits. Actually, nobody shouts it, but the famous Bertini and Ioannidis method is essentially using a functional Fokker-Planck equation, which is a bit of a nasty, it's not a well-defined quantity, but in the low noise limit, it's okay. So they actually used, I might, if I have time, I'll comment about it. But you use the Hamilton-Jacobi equation.
Okay.
And if I have time, I'll comment about it. That will tie very, very closely to the fact that for the steady state, we'll be interested in trajectories where the Hamiltonian is 0.
Okay.
And I might comment. If I have time, I'll comment. Okay, depending on how much you pull me towards more formalism or getting to some results at the end, we'll decide about it. Okay, other questions?
Okay.
Okay, so I'll upload the notes. By the way, if you find any typos in the notes, I'll be delighted to hear about them. Typos, mistakes, whatever, I'll be happy to hear. Okay, thank you very much.
Okay, see you tomorrow.